Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have AAS Journal author Ian Cohen with us today. Hey, Ian.
Hey, how's it going, Frank?
I am doing super well on this May 23rd of 2022 as we shoot this video. And so it's late May. Is it spring in Johns Hopkins, Baltimore?
It is. Spring is springing. Yes, it's been actually unseasonably warm, though. It feels like we went straight from late winter into summer, and it's a little soupy, but hopefully Memorial Day weekend will be lovely as it approaches and officially starts summer.
Awesome. I'm in Phoenix, Arizona, and yes, about 3 days ago or so, somebody hit the power switch. And so we got up to 106, which is, 35, 36, something like that, doing that conversion quickly in my head. And it's still pretty warm. So yeah, the power switch has been thrown in Phoenix, so it's all great.
Probably not too soupy, though.
Pardon?
Probably not too soupy.
Actually, the humid season in the Southwest is in the summer, because it's that Gulf moisture that comes rolling up from the south, and so we get that not as heavy as like Houston or something like that, but we definitely get that moisture coming up, and it's what drives the what we call the monsoon season here. So the rainy season in Phoenix is actually June, July, August. It's when we get our big thunderstorms. It's when the rains come down. And it won't dry out until we get to about October, September, October. So we have a nice, long, healthy, somewhat moist, hot climate. So very cool. What is your position there at Johns Hopkins?
So I am a senior professional staff member,
Awesome.
member of the technical staff at APL. I am now in our geospace and earth science group. It's a very recent transition, but I mostly do space physics. So studying the environment around planets, primarily Earth, but also now venturing into other planets, as we'll talk about with the paper that we just published.
That's right. And in fact, why don't we go ahead and get right to it, since you sort of said what your research was right there. And we have this very awesome and lovely Planetary Science Journal article. It's open access, people. You can go get it, grab it for free. The case for a new frontiers class Uranus orbiter, system science at unexplored and unique world with a mid-scale mission. And Ian, take us away.
Yeah, thanks. So this is the byproduct of a proposal that I was fortunate enough to lead with an international group of colleagues. So you can see a very large and diverse team that we pulled together across the United States as well as international institutions. And this was a proposal that went into the Planetary Predecadal Mission Concept Studies opportunity a few years ago. And so we were really trying to look at what it would take to go back to Uranus with specifically something that was designed to be less than a large strategic flagship. A lot of studies have been done to look at flagships, very big flagships that would do a lot of great science. And we really wanted to see whether or not we could do something on a mid-scale, so new frontiers on the order of about $1 billion. And cool. Because we're looking at a mission that was across the scale for the system, we really wanted to try to make sure that we had every sublet or discipline of planetary science covered. So we had magnetospheres, we had rings, we had interior, we had atmosphere, we had satellites. We were trying to get as much breadth in the team as possible.
Well, Uranus has it all, so you know.
It does. And even though summer schools like the Planetary Science Summer School and some other European colleagues have looked at kind of new frontiers, there had not been and still hasn't been a NASA-funded study to look in this wheelhouse. And so we were trying to make the motivation that we should do that. And one of the big things we were trying to say is in the last decadal survey, which came out in 2013, there was Uranus orbiter and probe was the third highest priority. It didn't look like that was going to happen in the last decade after Mars sample return got started and what now is Europa Clipper we're getting going. And so we're really making the case that we wanted to get back and see if we could try to do it possibly on a more cost-efficient approach. And in particular,
$1 billion is cost effective.
Yeah, well, it's expensive to get out to the outer solar system. And right now we know that the European Space Agency, ESA, is very interested in potentially collaborating on a future mission. There's been a lot of excitement from the outer planetary, especially the ice giant community over the last 5 years or so, to really try to galvanize as we got into the decadal survey and getting back to the ice giants and making it a large priority for the community. And so we were trying to rally around that and try to get this proposal in and this concept out into the community for consideration.
Cool. Very cool.
And yeah, and the big point we wanted to make, there were some ideas about, we've done a flyby with Voyager 2, that was over 30 years ago. We could get more information with another flyby. Maybe we fly by Uranus on the way to a Kuiper Belt object or something like that.
Right.
And we were really trying to make the case that you need an orbiter at Uranus because it's just such an oddball.
Yes, it is.
It's sideways.
Anyways.
Yeah, the magnetospheric environment is
exactly.
Yeah. The ring system is extremely dense and haphazard was uniquely dense and haphazard was the phrase that one of my colleagues came up and we used here. We think it probably has to do with the fact that it's had this tumultuous history that knocked it on its side. The ring system might still be in the process of reforming.
Okay. Yes.
So you don't get something that's as well established and easily defined as, say, like at Saturn.
Right.
And we were trying to make the case that every time we've sent our first orbiting mission to a planet, right? Messenger at Mercury, Galileo at Jupiter, hopefully, a future mission at Uranus. Even though we've done countless flybys at those planets, the first orbiter always shows us how much we were missing and how much we didn't know. Cassini, absolutely. Yeah. So it's, getting there, being there for an extended period of time and really being able to distinguish what's transient in the system versus what's the actual steady state of the system. It's really hard to do that when your flyby is of the same order or, possibly shorter than some of the scales of the processes that are going on in the environment.
Yeah. For example, if you wanted to see, long-term weather patterns or something like that, right? You're not going to get that on a 30-minute flyby.
Right. Yeah.
Very cool.
Yeah, and so this was our case for trying to outline what we could do with a potential mission like this. Because this largely stemmed from a proposal to do a concept study, we didn't have all the answers. We were just kind of trying to outline the possibility and make the case for why we should look at it more closely. And so some of the things early on, like the first figure, which really outlines what we could potentially do for science, we call this a proto-science traceability matrix because we didn't actually do the work of tracing out all the measurement requirements and everything, but we were really trying to make a case to the community about some of the really compelling mysteries at Uranus. And like I said earlier, we were trying to take a very holistic system approach, right? We weren't trying to hone in on just the satellites or just the interiors. We really wanted to get a broad swath and show how Uranus can be a rich target for everyone, right? If you like rings, there's something at Uranus for you. If you like energetic particles in the magnetosphere, there's something for Uranus at you. If you want to understand solar system formation, there's something at Uranus for you.
Absolutely. Very good.
Yeah.
So these are all the mysteries.
Yeah. And so then we tried to map those to actual science objectives, what we would want to do with a mission, even a mid-class one in New Frontiers, and then take that just one step further to say, at least at a high level, what are the things that we could look at to try to answer those science objectives? And normally, if you were actually putting together a proposal or putting together a concept study, you would take this one step further and actually say, to do these potential observables, this is what you need to measure. This is the precision with which you need to do it. We didn't take that step, but we did look at how this would map to potential payload that we could bring with us. And so that was in the second figure.
Oh, yeah. Sure. Let's take a look at payloads. Okay. Very cool.
You'll notice the same science objectives from the middle column above, and now mapping that to the different, not necessarily the measurements we would take, but the type of instruments we would use to make those measurements that would address those questions.
Yes.
And so you can see very quickly, you can get a very comprehensive payload that would weigh lots of, have a lot of mass, but you can pretty quickly see where
Yes.
certain instruments would start popping out because they have pretty broad applicability across the spectrum of science. And so this was kind of give us a sense of where we might want to focus more of our attention if we were going to do a study and try to prioritize payload that we were going to bring with us.
Okay. Mm-hmm. Mm-hmm.
And then we really dive into why we're trying to do, why we're trying to address all these different science objectives across the different subdisciplines of planetary science. And
cool.
I'm actually primarily work in the heliophysics community. Traditionally, I'm trying to get more involved in planetary science. And so it's interesting for me coming in. This was one of my first exposures to planetary science kind of at large. And it's just so fascinating to have so many different subdisciplines all working on the same mission, the same concept, the same target. You know, in heliophysics, we tend to focus on Earth primarily, and it's, you know, there's the magnetospheres community, and we're so deep in the weeds on the magnetospheres. You know, we don't talk all that much to the atmosphere folks, let alone, you know, the lunar scientists, let alone the hydrologists that are working on the surface, the earth science. So seeing how this community interfaces across those subdisciplines is really fascinating.
Beautiful. Mm-hmm.
And so if we scroll down, we can take some more figures here that talk about some of the things that make Uranus so attractive. And so if you're a satellites person, there are 5 classical satellites. So these are, you know, large enough to be spherical. Unfortunately, we don't know a whole lot about most of them. On order of about 40 to 50% of them have been imaged by Voyager 2. So there's lots of unknowns here. We do know that these are some of the darkest surfaces in the entire solar system. Why that is, we're not entirely sure. There's some conjecture that some of these worlds, specifically Ariel, might be a sleeper ocean world, right? It might be a place where we might want to explore habitability.
Yeah.
My geophysics colleagues tell me that Miranda in particular is very interesting. You can see that kind of Nike swoosh feature that's there that no one can quite explain. You know, how do you get any process that gives you something like that, whether it be fracturing or cryovolcanism? We're not really sure. And so a lot of folks are, and us included, are interested in getting back to the system to see what's going on with these moons. Are they potential ocean worlds? Why are they so incredibly dark? Part of that might be their interaction with the energetic particle environment around Uranus, which is part of the magnetosphere. And so that kind of segues us very nicely to the next figure there. So the magnetosphere of Uranus is, like most things at Uranus, very odd. So we know Uranus is on its side and rotating roughly with its rotational axis in the ecliptic plane.
Yep.
But the magnetic field has the largest offset from any planet in the solar system. So it's almost 60 degrees, almost orthogonal to its rotational axis. And so as the planet spins, you get this very odd sweeping out of the magnetic field. And, you know, it hurts my brain to try to think about what the magnetic field configuration might look like as you fly through the system, let alone how does that interact with the solar wind as it comes out from the sun? How does that interact with the moons, many of which you can see are actually outside of the magnetopause in their orbit? So just a fascinating magnetosphere for us to look at. It's still very open whether this is solar wind driven. So do the dynamics respond to the sun primarily, or is it internally driven by the rotation as well as potential sourcing of plasma from the moons? You know, we think that Earth is kind of the archetype of solar wind driving, whereas Jupiter is kind of the archetype of internal mass driving. We think Uranus might be a middle ground, but we don't actually know. And so it's fascinating to say the least, and we're hoping that we'll get back there to be able to understand what's going on. There's also an oddity, if you scroll down a little, the energetic particle regime at Uranus was surprisingly intense for what we expected, especially because there were not very many low energy particles seen by Voyager 2. Normally what happens when you have a radiation environment is you have a very robust low energy plasma source, and then mechanisms take that low energy plasma and energize it up into the higher energies. And so you have a very clear source of those energetic particles. At Uranus, we kind of saw the opposite. We saw very intense energetic particles, but no very clear source population. And so it's unclear where these energetic particles come from.
Yeah. Very interesting.
Part of the possibility is that Voyager just didn't have the right instrumentation to be able to really capture and characterize the low energy population correctly, but we don't know.
Okay, cool.
So then if we move on to figure 5, we have the interior, which is very largely unknown for us at the ice giants, because again, we only have about a 2-day period of observations from the Voyager 2 flyby. And there's a lot of pieces here that are kind of unknown. So we show some oddities that we don't understand. The upper left is the magnetic field that we know is coming from Uranus. We know it has an intrinsic field. This limited data suggests that there's very complicated, probably higher order magnetic field moments that are more dominant. So unlike Earth, Jupiter, Saturn, which are largely dipolar in their magnetic fields, there's probably higher order moments that are making the field more complex. Whether that's the internal composition of the moon, of the planet, or its tumultuous past, we're not really sure. That feeds into what we think the interior looks like in figure B there. Do we have a very well separated interior where you have a core that is well separated from something like a mantle versus a crust? Or is it a much more gradual change in composition where things kind of get maybe a little slushy, if you will, if we really have ices in there?
Right, differentiation.
Yeah. And then last but not least, there's always this question about energy balance with the giant planets. Yes. And so it's unclear whether or not, with the limited information that we have from Voyager 2, it seems like Uranus actually emits a lot more energy than it absorbs, which is very odd. Again, an oddball in the solar system in that sense. We're not sure where that giant peak at 0 degree latitude and emitted energy comes from. Not sure. If I put on my skeptic, my crazy ideas hat, maybe whatever hit Uranus and caused it on side has locally heated it, and we're still emitting that rim. I don't know. Not an interior scientist or an atmospheric scientist. But the interiors, this is one of the things in particular that a future mission, whether it be New Frontiers class or flagship, would really want to try to figure out is what is the interior of our local ice giants like? How did they come to be in the solar system? Did they form out where they are? Did they start much further out and migrate in? We don't really know. The
great tack.
Yes. All right. Figure 6. So last but not least, we'll talk about the atmosphere and the rings. Because everyone loves atmospheres and rings. So on the left, you can see the many faces of Uranus. Voyager 2, the flyby imager, the white light imager, figure C. It looked kind of bland, if you will, right? Not too exciting. Especially when you compare to the images of Jupiter, Saturn, and Neptune, where you have this very clear storm patterns and banding and all of that. You could assume that Uranus is maybe a little less compelling. But once we look at infrared and ultraviolet and some of the other different wavelengths, you start to see in A and B that there are localized hotspots. We've seen Hubble images that show us that there are aurora on Uranus. There's lots of the banding pattern, especially in the infrared. There you can see what look like localized storms. Part of it's probably because it's smaller, right? And so the image, the light is not in the visible infrared because it's smaller and cooler.
Right.
Yep. And then under this is one of the big questions in atmospheric science. We have no idea how atmospheric circulation works in Uranus. Part of that is because we just haven't gotten very good, especially low altitude observations. Part of the reason why we'd like to go in with an atmospheric probe, try to get some of the noble gas ratios, is again feeding back to the origin question and the formation question. Now, one of the big things about a mission that we try, if we were trying to do something mid-scale, We probably wouldn't be able to carry a very large Galileo-like, 300 kilogram atmospheric probe that would be able to get all the science that we want.
Right.
And so we were trying to make a case that we could do a lot of great science without that atmospheric probe, not totally precluding the idea of maybe carrying something much more focused in capability
Right.
to get that information. I think everyone would agree that some information, even if it's limited, is better than no information.
Absolutely.
But questions like, is there a 3-cell circulation pattern at play at Uranus was something that we were going to try to go at, especially possibly looking at like infrared emissions, possibly as well as UV.
Okay.
Yeah. And then last but not least, for the rings and small moons, this is a really great figure that my colleague Richard Cartwright made, especially for this paper. But looking at, as Richard, or sorry, not Richard Cartwright, sorry, Robert Chancia, sorry, totally mixing up a colleague's name. Rob Chancia made this figure. And Rob really came up with this idea, this term, uniquely dense and haphazard for the ring system. You can see how busy it is once you get inside the orbit of Miranda. You have the outer mu ring, which we know is very blue. There's also the new ring, which you can see in the Portia group is very red. So how do you get this very stark differentiation in colors between rings that are pretty close to each other? And then there's lots and lots of small moons. I think there's about 13 or so, including Puck, which is one of the largest. And so, especially if we want to be able to do an orbiter mission where we're going to be close to the planet, we need to characterize this area very well so that we know whether or not we're going to worry about hitting something.
Yeah.
And this probably holds a lot of this region probably holds a lot of the keys to the history of the Uranus system. Why is it so densely packed? Is the ring system still in the process of reforming after possibly, a cataclysmic event in the system? We really don't know.
Yeah. Beautiful figure. Very nice.
Yeah, it's one of my favorites. And we pushed really hard to make sure it got published so that Rob could get all the credit for making it.
Lovely. Very nice.
And so then, we wanted to talk, given all the great science that we wanted to do, we were really trying to motivate how we would do this in a New Frontiers class. As I said, a lot of studies have looked at very large scale missions that have very large price tags associated with them, have required a lot of plutonium for power. That's a major problem as we look forward to exploring the outer solar system. How do we, make sure that we have enough plutonium to do these missions, as well as use them in very efficient ways? The most recent radio power or radiothermal, radioactive power systems are not the most efficient, and so it requires a lot of them, which requires a lot of plutonium. We don't have a giant stockpile sitting around at the moment, unfortunately.
No.
And so how do we get more efficient while also increasing production on those was something that we were really trying to focus on with the study. And then going back to the question earlier about what the payload would look like, we, without doing too much of the study work, which was what we're hoping to make the case for, we think that something on the order of 50 or 60 kilograms would be reasonable for us to be able to fly. And so we kind of, based on the mapping figure in figure 2 that showed all of those different payloads that we could potentially bring, we tried to figure, this one here, kind of taking a look at what you needed for certain science and where you could get the most bang for your buck, literally, across the science. We tried to figure out what instruments we could potentially bring and how that would compare to, a rough 50 or 60 kilogram estimate. And so that's what figure 8 is. It's really showing kind of a notional payload, not trying to prescribe anything, but, if we brought a payload, what would we potentially be able to do? And so we tried to balance in, imagers, especially visible and near infrared, something that could get spectrographs so that we could get composition information, as well as the in situ plasma and field suite. Possibly, if we added in and went a little bit beyond our 50 kilograms, we could bring something like a NAC that would really get high resolution images of the rings and satellite surfaces, as well as possibly an ultraviolet spectrometer and a thermal infrared imager. And this puts us at, about 62 kilograms, 62 watts, which we thought was in the realm of feasibility without having done very comprehensive engineering study.
Yeah, deep. Mm-hmm.
And
good.
And so that was the case we were making. We did talk quite a bit about some of the previous studies that have been done, especially in trajectory design, how we could get to Uranus, how we could take advantage of the well explored trade space for trajectories, that we might be able to actually bring something with a fairly comprehensive payload for a cost-effective bottom line. We also talked about the fact that we might look at aero capture. That's something, basically using the atmosphere to put yourself in orbit. That's a very potentially risky approach, because especially if you don't know the atmosphere very well, if you're off by a little bit, it can be very problematic, to say the least.
What is the what would be the lifetime of such an orbiter?
Yeah, so we were looking at a baseline, and what you plan to versus what you hopefully get in the end are always very different. But we were hoping for at least 2, maybe 4 years in orbit. Part of that depends on the trade between how quickly you can get there with your trajectory, as well as the planned lifetime of the RTG systems. So a lot of the RTGs are kind of designed to a 17-year shelf life. So you lose a year or so right off the bat just in the process of building it. And then once you're basically launched, you have about 15 years or so. So some trajectories can get you there as fast as 11 years, which would leave you about 4 years in orbit. Some take as long as 13 or 14 years, which would leave you something more like 1 or 2 years.
Okay, got it. So power, supplying energy is a key.
Yep. Yeah, and as with most things in the outer solar system, you have the 3 Ps: power, propulsion, and communication. When it's your power through your transmitter.
Yep. Interesting. Cool. Oh, here we go. Okay, that's what I just asked. Very good. Very cool. Very cool. Well, Ian, thank you so much for walking us through your very lovely PSJ article.
Thank you.
And you
happy to talk about it.
Yeah, everybody loves talking about their articles. So you touched on it a little bit, and so I'll ask you to push on it a little bit. Where do we go over the next couple of years? Presumably there's another decadal survey coming out, so maybe this was mentioned, but where do we go over the next couple of years in making this a potential reality?
Yeah, so one of the big things we tried to push with this study was to try to get back before the equinox. So basically the spring equinox, once the unimaged part of the moons go back into shadow. So that happens roughly around 2050. And so thankfully, the decadal survey, which just came out a few weeks, actually has a Uranus orbiter and probe as the highest priority large scale. Yeah, going back, hopefully, fingers crossed. And so, even though the decadal recommended a flagship that would have an atmospheric probe, the case that we outline here is certainly not entirely moot, because the science is still very relevant. And I think even future flagships are going to need to be a little bit more efficient in how they approach things. And so trying to adopt some of the design elements that we highlighted here will probably be similarly appropriate for a future flagship mission.
Yeah, very cool. Very cool. Well, that's fantastic news.
Yeah.
Wonderful.
We're very excited.
We're very happy. That is great. That is great. Awesome. Ian, thank you once again for stroke on Uranus. Very nice. Thank you.
Thank you.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.